Hello everyone. Today we are going to talk about the topic of gallium nitride in EV charging stations and storage ready inverters. This was done by myself Ashwat Sivarajan, Krishna Narayanan and Kavi Kumar. Let me tell why we choose the topic of gallium nitride in EV charging stations and storage ready inverters. Like it increase the efficiency. Gallium nitride is a wide bandgap semiconductor material that offers superior performance compared to traditional silicon-based power electronics. Gallium nitride device has lower power conduction and switching losses, enabling high efficiency in power conversion system. By implementing gallium nitride technology in EV charging stations and storage inverters, you can significantly improve the overall energy conversion efficiency, resulting in reduced power losses and increased system performance. It has high power density, like gallium nitride devices can operate at high voltages and currents while maintaining compact form factors. The characteristics makes them well suited for applications that require high power density, such as EV charging stations, energy storage systems, etc. By integrating GaN technology, you can design more compact and lightweight charging stations and inverters, enabling easier installation and reducing space requirements. It has fast charging capabilities. One of the critical challenges in electric vehicle adoption is the time required for charging. GaN-based charging stations can deliver high power levels, allowing for faster charging rates. With GaN technology, you can potentially achieve high charging power while maintaining efficiency, enabling shorter charging times and improved convenience for electric vehicle owners. It has future-proofing for energy storing integration. As the demand for energy storage systems continues to grow, it becomes essential to have inverters that are compatible and storage ready. GaN technology enables the design of inverters with high frequency and switching capabilities, which are suitable for integrating energy storage system. By implementing GaN in storage ready inverters, you can ensure that the inverters are capable of efficiently integrating and interacting with energy storage devices in the future. Electric vehicles and renewable energy sources play a crucial role in reducing the greenhouse gas emission and combating climate change, enhancing the efficiency and performance of EV charging station and storage ready inverters. Through GaN technology, we can contribute to the wider adoption of electric vehicles and renewable energy system. This project aligns us with the goal of sustainability and environmental responsibility. Overall, selecting the project of GaN in EV charging station and storage ready inverters offers the opportunity to leverage the advantage of GaN technology, such as improved efficiency, high power density, fast charging capabilities, and future proofing for energy storage integration. It can contribute to the development of more advanced and efficient system for electric vehicle charging and energy storage, driving the transmission towards the greener and more sustainable future. The outline of the project we are going to talk about are: first one is topology of GaN storage inverter, second is working of GaN inverter, third control objectives. In control objectives we are talking about control variables and need for control, then overview of controller, and then summary. Now I am going to talk about topology of inverters. When it comes to GaN based storage inverters, various topologies can be employed. Choice of topology depends on factors such as power requirements, efficiency goals, and system constraints. Here are few commonly used topologies for GaN-based storage inverters, like full bridge topology, off-bridge topology, multi-level topologies, bridgeless power factor correction, resonant topologies. Full bridge topology. The full bridge topology is a widely adopted configuration for GaN-based storage inverters. It consists of 4 switches arranged in a bridge configuration. The configuration allows the bidirectional power flow, enabling efficient energy transfer between energy storage system and the AC grid. GaN devices can handle high voltages and currents, making them suitable for this topology. Next is half-bridge topology. Half-bridge topology is another option for GaN-based storage inverters. It utilizes 2 GaN switches arranged in half-bridge configuration. This topology is often used in lower power applications and provide good efficiency. However, it does not support bidirectional power, uh, like full bridge topology. Multi-level topologies. GAN devices, power switching speed and high voltage capabilities make them well suited for multi-level inverters. Multi-level inverters are several power switches to generate step approximation of sinusoidal waveform. Topologies such as diode clamped inverter or cascaded H-bridged inverter can be implemented with GAN devices to achieve higher power levels, reduced harmonic distortion, and improved efficiency. Then, bridgeless power factor correction. Power factor correction (PFC) is an essential requirement for power converters to ensure efficient power on the grid. GAN devices can be employed in bridgeless PFC topologies such as bridgeless boost converter or bridgeless buck boost converter to improve power factor and reduced conduction loss. Then resonant topologies. GAN devices as high frequency switches capabilities make them suitable for resonant converter technologies. Topologies like inductor capacitor or LCC inductor capacitor converter can be implemented with GAN devices to achieve high efficiency, reduce switching losses, and improved power density in storage inverters. It is important to note that choice of topology of GAN-based storage inverters depends on various factors including system requirements, efficiency goals, cost consideration, and control complexity. Each topology has its advantages and trade-offs, and selections should be based on careful evaluation of the specific application requirements and constraints. Next, working of the GAN inverter can be explained by Mr. Narayanan.
Thank you, Ashwat. I am myself Krishna Narayanan, and I am here to explain about the working of storage inverter, which is based on gallium nitride. So yeah, let's go. Gallium nitride power devices. It is basically a semiconductor material that has several advantages over traditional silicon-based devices. Gallium nitride power devices such as gallium nitride transistors are used in storage inverters due to their superior performance. These devices can switch on and off rapidly, enabling high frequency operation. We go into control circuitry. So control circuitry is responsible for managing and regulating the power flow within the inverter. It consists of various components including microcontrollers, sensors, and feedback loops. The control circuitry continuously monitors the input voltage, output voltage, and current to ensure efficient operation. Energy storage system. So the energy storage system is a crucial component of GAN-based storage inverter. It typically consists of a battery which can store electrical energy generated from renewable sources like solar panels or wind turbines. The battery acts as a reservoir, storing excess energy during time of low demand and releasing it when there is a need for power. DC to AC conversion. The gallium nitride based storage inverters converts the DC stored in the battery into AC used to power our homes and devices. The conversion process involves several stages. Step 1, it goes like the DC input, the DC power from the battery is fed into the inverter. The next step is power conversion. The gallium nitride power devices, specifically the gallium nitride transistors, are controlled by the control circuitry to rapidly switch on and off. This switching action converts the DC power into high frequency AC power. Step 3, it's filtering. The AC power output from the gallium nitride power devices is typically a high frequency square wave. To make it suitable for powering appliances and devices, the output is filtered to smoothen the waveform and remove any unwanted harmonics. Finally, the output voltage regulation, which is very important. The control circuitry continuously adjusts the switching of the gallium nitride power devices to maintain and stabilize the output voltage. This ensures that AC power supplied by the inverter matches the required voltage for the connected load. So, grid interaction. In many cases, the gallium nitride based storage inverter is also designed to interact with the electrical grid. It can work in grid connected mode where it synchronizes its output with the grid frequency and voltage. This allows the excess energy which is not going to be used by the load to the grid. This allows excess energy generated back to the grid, helping to stabilize the overall electricity supply. Overall, the gallium nitride based storage inverter combines the advantages of gallium nitride power devices with efficient control circuitry and energy storage system to provide a compact, high efficiency and efficient solution for converting stored DC energy into usable AC power. It offers improved power conversion efficiency, reduced size and weight, and increased reliability compared to traditional inverters. That's all into working of the storage inverter. Let's get into variables to be controlled. Gallium nitride storage inverters, several variables need to be controlled to ensure efficient, reliable operation. Here are some key variables that are typically controlled in gallium nitride based storage inverters. The first thing is input voltage. The input voltage to the inverter, which is usually derived from the energy storage system, basically battery, needs to be regulated. Controlling the input voltage ensures that the inverter operates within its specified voltage range, optimizing the power conversion process. Output voltage and frequency. Output voltage and frequency of the AC power generated by the inverter must be controlled. These variables need to be regulated to match the requirements of the connected load or the electrical grid if the inverter is grid connected. Precise control of output voltage and frequency ensures compatibility and reliable operation of the devices or grid connected systems powered by the inverter. Power conversion efficiency. Controlling the power conversion efficiency is influenced by factors such as switching frequency, modulation techniques, and control strategies employed in the inverter. Optimizing these variables helps the maximum efficiency of the power conversion process, reducing losses and improving overall system performance. Inverters need to be limited and protected from the current overflow through overloading or damaging the inverter or the connected load. Implementing current limiting and protection mechanisms ensures safe operation and protects the system from potential faults or short circuits. Maximum power point tracking (MPPT). In a power-based storage inverters, MPPT is essential for extracting the maximum power from the solar panels. MPPT algorithm continuously tracks the solar panel's operating point and adjusts the inverter's operating parameters to maximize the power output. Controlling variables such as input voltage and current based on MPPT algorithm optimizes the solar power harvesting efficiency. Grid interfacing and synchronization. For grid connected gallium nitride based storage inverters, variables related to grid interfacing and synchronization need to be controlled. This include parameters such as grid voltage, frequency, phase synchronization, and power factor control. Accurate control of these variables ensures seamless integration with the electrical grid and compliance with grid standards. These basic variables needed to be controlled through the use of microcontrollers, basically C2000, which implement control algorithm and adjust the operation of gallium nitride based power devices and other components with the inverter. The control algorithms are typically implemented using the programming language such as C or Code Source Studio for precise control and optimization of these variables in gallium nitride based storage inverters. Thank you, and here is Kavi Kumar to overtake the upcoming topic.
Hi, I am Kavi. Let's discuss about the need for control and overview of the controller. In a storage inverter system, control is crucial to ensure efficient and reliable operation. The C2000 microcontroller is commonly used in power electronic applications, including storage inverters, due to its real-time control capabilities and integrated peripherals. Here's why control is essential in a storage inverter and how the C2000 microcontroller facilitates it using C programming. Power conversion control. A storage inverter converts DC power from a battery or energy storage system into AC. Precise control is required to regulate the voltage, frequency, and waveform of the AC output. The C2000 microcontroller, with its high-performance analog to digital converters and pulse width modulation, enable precise control of the power conversion process. C programming allows developer to implement control algorithms to regulate the inverter's output based on system requirements. Let's talk about the MPPT, maximum power point tracking. In solar-based storages, inverters is employed to extract the maximum power from solar panels. MPPT algorithms continuously track the solar panel's operating point and adjust the inverter's operating parameters such as input voltage and output current, to maximize the power output. The C2000 microcontroller, with its computational capabilities and analog interfaces, facilitates the implementation of MPPT algorithms in C code. Grid interfacing and synchronization. Grid connected storage inverters require control to interface with the utility grid. Control functions ensure synchronization of the inverter's output with its grid voltage, the frequency. The C2000 microcontroller, along with its communication peripherals and control capabilities, enables precise grid synchronization. C programming allows developers to implement grid interfacing algorithm, communication protocols, and safety mechanisms required for grid connected operation. Energy management and state of charge estimation, that is SOC. Storage inverters often incorporate energy management system to optimize battery usage and prolong battery life. Control algorithms are necessary to monitor the state of charge of the battery, estimate its remaining capacity, and regulate charging and discharging process. The C2000 microcontroller, analog to digital controllers, timers, and computational capabilities allow developers to implement SOC estimation algorithms and energy management control logic. Fault detection and protection. To ensure system safety and reliability, storage inverters require control mechanisms for fault detection and protection. This mechanism continuously monitors various parameters such as voltage, control current, and temperature, and detect abnormal conditions or the faults. The C2000 microcontrollers integrated fault protection features such as analog comparators, interrupt handling, and fault detection modules aid in implementing fault detection and protection algorithms. By utilizing the C2000 microcontroller's real-time control capabilities, integrated peripherals, and C programming language, developers can implement sophisticated control algorithms, regulate power conversions, optimization energy management, synchronize with the grid, and ensure fault protection in storage inverters. The combination enables efficiency and reliable operation of the storage in inverter system. Overview of the controller. Certainly, let's elaborate the code and its relationship with converters, and then discuss how the code works. The code snippet is likely a part of large program that involves controlling a power converter. A power converter is a device that converts electrical power from one form to another, such as converting DC to AC or vice versa. The code forces a configuring and controlling certain aspects of the power converter. Clock and configuration. The code begins by configuring the clock and enabling specific functionalities. This ensures that the microcontroller operates at the desired frequency and sets up the necessary setting for subsequent operation. PLL, phase locked loop. The phase locked loop is a component that helps generate a state clock signal in this code. The PLL is configured by setting specific values to PLL-STS and PLL-CR registers, ensuring that the microcontroller has a stable and accurate timing reference. Timers and interrupts. Timers and interrupts are crucial for precise timing and event handling in a power converter system. The code initializes and configures timer to setting its period and other control registers. It also installs an interrupt vector to handle specific events or actions triggered by the timer. GPIO, General Purpose Input Output. To control an external device, GPIO pins are used to interface with the external components such as switches, sensors, and other power converter circuits. In this case, GPIO pin is used to control the state of external device based on the calculated result. Interrupt handler. The interrupt handler function is responsible for performing specific operations when an interrupt is triggered by timer 2. Inside the function, calculations and operations are performed using the variable and constants. The calculated result is used to determine the state of GPIO pin, GPACT or GPACLER. Controlling an external device, if the calculated results certain conditions, the GPIO pin is set high, otherwise it is cleared. Code flow and control. The code includes the control flow statement such as conditional statements and loop that dictate the execution path and behavior of the program. These statements allow the code to make decisions based on calculated values and control programs flow accordingly. Let's sum up with the summary. A GaN-based storage inverter is a device that converts the stored DC energy to AC GaN power devices, that is a gallium nitride, such as GaN transistors, are used in these inverters for their superior performance. The working of a GaN based storage inverter involves several components and process. The energy storage system, typically a battery storage electrical energy generated from renewable sources. The DC power from the battery is converted into highly frequency AC power using GaN, controlled by a microcontroller based circuitry. The output AC power is filtered and regulated to match the required voltage for the connected load. The GaN based storage inverter can also interact with the electrical grid, synchronizing its output with the grid's frequency and voltage. This enables excess energy to be fed back into the grid. Overall, GaN based storage inverters offers advantages such as improved power conversion efficiency, reduced size and weight, increased reliability compared to traditional inverters. These inverters play a crucial role in enabling the efficient utilization of stored energy and facilitating the integration of renewable energy sources into the electrical grid. Thank you.